I will explain backpropagation from scratch with all of these cool animations so you understand all of the intuition behind it, and you will be able to do it by hand and math. All of it, it's very interesting, it's very fun. The math is fun, and this is all that a high top level AI research scientist and engineer must know. I want to first draw some vectors. So we have vectors 3, 1, 1, 2, etc. So this is the vector, the blue one is 3, 1, 3x and 1y. And we have all of these other vectors. If you multiply all of these vectors with this matrix 2, 0, 0, 1, this will pull double the x coordinate. So this will be 6, 1. Let's just see before we go deeper. So you see it's gonna just double every x coordinate. And in this case, it doesn't matter if you multiply this row with this row or this row with this column, because it's symmetrical. So it doesn't matter if we transpose or not transpose, we will get same new vectors, same transformation, same linear transformation for these vectors. Just a short note. So the way this is multiplied is, imagine this is a column vector. So this column gets multiplied with this row, and that gives you x coordinates. And then this gets multiplied with this row, and that gives you y coordinate. So if you want to calculate this manually and check how that works, this one is not symmetrical, so I want to tell you how it's being calculated here. Let's see, we have this matrix 1, 3, 0, 1. So this controls x, this controls transformation of x, this controls transformation of y coordinate. And let's see, we have a bunch of different vectors. You will notice that every vector gets pulled and transformed differently here. For example, this one doesn't move. And this long one gets elongated most, and these other ones don't get elongated so much. So this is how this matrix transforms the vector. Y is gonna be the same because it's 0 times x plus y 1 times y, so y doesn't change. But x is now becomes x plus 3y. So with this, I just want to show you that these matrices rotate x and y vectors or stretch or pull based on some combination for both of them of x and y. Let's check this one out. What do you think this will do? 10, 0 and then 0, 1, 0, 1. We can check the animation. You see x gets pulled a lot, but y gets squished. And this is the formula. So the new x becomes 10 times bigger than initial vectors x, and y, new y, becomes 0.1 of x plus 0.1 of y. So now, these vectors, what are they actually? They are our weights in the neural network. So in reality, and this is a bit confusing, but bear with me, these vectors are actually also stretching and transforming input vectors or numbers. So now in our example, these weights are getting stretched by some other matrices, but we use these vectors to also stretch and transform inputs, so they are also being used as stretching vectors and transformations. Let's explain on an example. So we have this vector green one, 1, 2. So it's this vector, 1, 2. So during our training, as I was showing to you, we are stretching, moving, reflecting, rotating this vector. We are trying to find the correct weight. And the goal of that weight is also to stretch and transform the input to our neural network, so we get the output. So let me recap just once more. X is the input to our neural network, the data we have. Y, this 11, is the output that we also have. We have input and output, and we are trying to discover the weights. the rules that will let us learn how to map input to the output. So later when we just have inputs, we can predict the output. So yes, this weight is transforming this vector into the output, but also we are going to find this weight by transforming it with some other matrix or some other vector. Now let's see how this works step by step, how to get to the update matrix from the beginning, and then how muon optimizer changes the update matrix and then applies to the weight. If you are confused, don't worry. So in the beginning we have this x input data and we have this true y. We know that it should be 11. Okay, and let's now pretend we don't know which weights we need. We don't know which weights will map from x to y. So first we will multiply this x with some random weights. We can just initialize them. And we get 7.5 as the output. But we know that the true output is 11. So how do we change these weights to make this 7.5 go towards 11? So for that we will use derivatives and partial derivatives and gradients, the fancy words. So I will try not to confuse you. So this loss function will calculate the difference between our calculated output and the true output. But it will not be just 11 minus 7.5. It will not be like that. We will have a better way. So we will use a better formula that will even have stronger amplification of the error. So this is the error, but we will square the error, so we get even stronger signal. So the further away we are from the correct prediction, the bigger error will be, and we will know, that we need to take even bigger step or to change these weights even stronger. And we can do the same thing without squaring, just by subtracting 11 minus 7.5. But square will make that error even stronger. So we will have even more signal that we need to take a big step or change these weights a lot. Okay, so how do we know, should we increase these weights, should we decrease these weights? This is a funny thing in mathematics. Okay, so you have these two numbers, and the y true is constant number, never changes, it's 11. That's the correct prediction. But this predicted number is changing. So with this thing called derivatives, we can calculate how to change this y prediction to make this go towards 0. So derivatives will let us calculate how to make this go towards 0, or more precisely, how this number changes as we change y. And y is dependent on our weight vector. So this is the real variable that we control. So to calculate how y changes, we need to just calculate its derivative with respect to this weight. This is the weight. So x is constant, this is variable. So we can calculate derivative of y with respect to this variable. So, and then we can just multiply two derivatives. So this is the chain rule. So it goes like this. Since we can only control this weight, and we want to make this loss go towards 0, so that means that this 11 is same as this output here. We first find how this loss changes as y changes, and then multiply that with how y changes as the weight changes. So just multiply the two derivatives. That's the chain rule. So then we will have how loss changes as this weight changes. So how to change this weight to make this loss go towards 0. So this is the same thing written just in fancy mathematics way. And not to confuse you, I will not read this as partial derivative, but I will just read it as derivative, as I was explaining. So the reason they wrote here partial derivative is because, there could be more variables here, not just this w. There could be like bias and other variables. So it's written like partial derivative of this with respect to this w. But now we just have this one variable. So we can also just say derivative. So it's not a partial derivative. So let's get back. What does this mean? It means derivative of loss, so this number, with respect to the weight. So it means like, how does loss change when we change the weight? We calculate that by first calculating derivative of loss with respect to y predicted, and then times derivative of y predicted with respect to the weight. So what I was just explaining. So now let's see how to take these derivatives. So if you remember your high school math, this should be easy. Or if you escape the classes, don't worry, we will learn it now. So there are some rules when taking derivatives. So if we have derivative of loss with respect to y predicted, so this is the function. So how do we take derivative? Well, first, there are two functions here. The first function is y pred minus y true, but there is outer function that's squaring and taking the half. So how exactly do I know that there are these two functions? I'm not sure. Like, there is this feeling that these are two functions. So basically, when you are squaring something, you need to see what you are squaring. So whatever you are squaring, you need to apply the rule of deriving from square to whatever it's squaring separately. So because we are squaring this whole thing, we will now look at this as like one variable, one thing, and apply the square rule. So that's the first function, which also includes this 1/2 in the first function. And after we process this square and 1/2, then we will look at this inside function separately. So maybe we can watch some YouTube videos on derivation. So we can replace u, these brackets, with u. And so there is the rule. The rule goes like this. If you have some, whatever you are squaring, the square goes in front. So now it becomes, so derivative of u squared is just 2u. And the 2u times 1/2, 2 and 1/2 will cancel. So you just get u. Okay. And then we have the inner function. So the inner function goes like this. You just have variable minus constant. So whenever you have constant, which also includes the sign in front of it, it just disappears, or it becomes 0. So plus 0 minus 0, it just disappears. And wherever you have a variable, you just put whatever the variable is multiplied with. So in this case, it's 1 times this variable, because there is nothing here. So it just becomes 1. So 1 minus 0. So this becomes 1 minus 0 when you take the derivative of u with respect to y pred, which means like you are looking at y pred as the variable and y true as the constant, because it's written here with respect to y pred. So because you separated these two functions, now we need to apply the chain rule, which just says we need to multiply the both derivatives. So let's see here. The first, which u, that was just this thing in the brackets. So we put the thing in the brackets times 1 in the second derivative. So that's just this thing in the brackets as the derivative of loss with respect to y pred. So that's the formula, but we have numbers in our example, so we can just replace the numbers, okay? So the final result, the derivative of loss with respect to y pred is minus 3.5. But as you remember, we also need derivative y pred with respect to weight, and then later multiply this and this. So there is a lot of like this decomposition based on the chain rule. But anyways, just stick with me, bear with me. Okay. So what this minus 3.5 means is that if we increase this y pred, which is this 7.5, by a small amount, then this loss will decrease by 3.5 times that amount. So just to recap, if we increase y pred by a small amount, it will decrease, the loss will decrease because it's minus by 3.5 times that amount. And remember, the loss function is not this is the derivative. The loss function is here. So you can try increasing by a small amount 7.5 and subtract 11, like you need to square and everything, but only do it for a small amount. If you add like whole number like 1 to y pred, then derivative will also change, so it will no longer be minus 3.5. So you just can test it with a very small number, 0.01 or something. Even that small number will change the derivative, but that will not be noticeable. So these are the things that you just need to kind of practice. There is a lot of YouTube videos on derivation, and you just need to practice and see what happens. And I'll make more videos so you can watch them. So after this derivative of loss with respect to y pred, we need to take y pred with respect to weight. And you know that weight is a vector, and it's getting multiplied by x vector. So let me go up. So here, how do we take derivative of this result with respect to these two vectors? And this is the only variable vector. So it was a just dot product. So it was first weight times x1 plus second weight times x2. So it was a simple dot product. So a bit more derivation. So how does result change with respect to w? As I said, when we multiply the variable with some constant, which is x is 3, then this becomes just number 3, the constant. And this constant, because we look at this now as a constant, all of this, like this w2. So all of this becomes 0 because it's a constant. And the reason we look at this as a constant is because we are looking for partial derivative of y pred with respect to w1. So only this term is a variable. So the derivative is going to be 3, 4. So derivative of y with respect to the w. And it seems to be very simple. And it makes sense. So how does this w1 change? Well, it just gets multiplied by 3. So its change is just times 3. So the derivative is 3. And w2 gets multiplied with 4. So the change is 4. 4 times w2. So the derivative is 4 with respect. So if we change the w2 by a bit, the result changes 4 times that bit. And for w1, it changes 3 times that bit. And because it's positive, it means if we increase w, the result will increase for both of the w1 and w2. And then apply the chain rule as I was explaining. So we need loss with respect to the weights. So it's going to be loss with respect to y prod times y pred with respect to weights, which we had both of them. We just get these numbers that we calculated, and this is how each of the weights changes loss. So that's it. Now we know how loss is going to change as we change w by a bit. And we want to change w such that loss goes down towards 0. So let's calculate some numbers. Let's see how much this numerically actually changes loss. The first one says if we increase W1 by some small amount, the loss will increase by minus 10.5 times that amount, so decrease because it's minus. And same for the second weight, it will decrease by 14 times that small amount that we increased the W. Now let's say we change both of the weights, we add 0.01 to both of them. Now we can just change one, or we can change them with different numbers. But let's see what happens in this case. So we just multiply the rate of change for both of them. And we get that changing the first one by adding this will decrease the loss by this amount. And second one will decrease the loss by this amount. So in total, the loss will be decreased by this total amount of both of them. Now I want to teach you something. So we will look at this function. So this is a squared quadratic function. So on x-axis we have the weight, and on y-axis we have square of weight. So let's say this is the loss function. Now it's different from our loss function that I was explaining. So you can imagine this as we get loss on y-axis depending on the weight, the W. That's loss does depend on the weight. So as y increases or decreases, loss becomes square of the y. Weight, W, weight, loss becomes square of the weight. So derivative at any of the points will tell us the steepness of the curve. So up here, derivative will be larger number because the curve will be steeper. And as we go down, we will notice that derivative, the curve becomes more flat, not so steep. So the derivative, so this means up here, at the more we change weight, the more this function will change a lot more. But in here, if we change a bit the weight, the function will not change so much. So the derivative of w squared is 2w, which means when we are on these higher w values, the derivative 2w becomes higher because we are, the higher we go, the double 2w will become even larger. So the derivative will be bigger, so the curve means the curve is steeper. Our goal is to find value of w such that loss is 0 or as close to 0 as possible. In this case, it can be 0. So we already see from this graph that when w is 0, that loss is also 0. But if we don't know that, if we are standing here and we just see that at this place the derivative is steep, what we can do is we can take a step proportional to the derivative. So if the derivative is bigger, it means it's steeper, it means we are further away from this 0. So the steeper the derivative, we can just take that much of the step down. Because the steeper the derivative, the further away we are from the loss. So just a quick note, this is because this function is very nice. So this function, the steeper it is, the further away you are from the 0 at loss. But what if function is like, goes like this, but then a bit flat, but goes like this, goes up, goes like this. So then it's not so clear that on this, so because this flat part can also be very far away from the 0, but derivative there would be very low, close to 0. So by this logic, we would just need to move a bit. But okay, so on this nice function it works. On this nice function, the steeper the derivative, the higher the derivative, the further away we are from the 0. So we can use that derivative to take the bigger step, because it just means we are farther away because the derivative is big. So when we are deciding the new value of the weight, we can just take the old value and subtract the derivative itself. And as I said, the bigger the derivative means the steeper means further away we are on this function from the center, so it works, it basically helps itself. So we started here and we made a big step if you look at the x-axis at the weight, and then smaller and smaller and smaller because the steepness is fading out, and we are just subtracting the steepness value itself because steepness value is actually showing how far away we are from the minimum on this nice function. But you will notice that we multiply the derivative with this term. So this is 0.2. So actually we need to scale down the value that we subtract, because if we subtracted full derivative value, then we would subtract way too much. So we would go way like overboard into negative, and then the loss would be a lot higher. So we would overshoot too much. So we multiply with this learning rate, small number, to go step by step. Okay, and here is what happens if learning rate, same thing, but just the learning rate is a bit higher. Instead of 0.2, it's 0.85. So you see now, going from this weight, we subtract and we land here to this weight. So here loss is this, okay? And now it's less steep. So now we subtract, go here, here. So now this is also converging. It's just we are making bigger steps because learning rate is higher, but this is still converging. But what if learning rate is too high, 1.1 in this case? Now what happens is actually the first weight we subtract, we actually go too much where the loss is higher now. So now we go too much, and then the next will go too much again, even more. So now this is diverging. So now learning rate is too big because we are subtracting too much, we are moving weight by too much. So this is gradient explosion. So that will be backpropagation from scratch. Thank you for watching and see you in the next video on our road to highly skilled AI researcher.